Okay, we're now looking at 19.24. It's a very similar problem to the last one, except we have an adiabatic expansion. So just for reference, I think I've got this here. Come on. Whoops. Pointing at the whiteboard does not work. I have the results of the last problem right here. So hopefully what we could do is we can compare the first law results and what the process looks like for an isothermal, which was number 19.23, to this to what we're doing now. So we'll come back to this and we'll do the comparison at the end. But right now, it's very similar input parameters. The only difference from the last problem is now it's expanding adiabatically. All right. So let's go ahead. Pause the video if you want to do everything yourself. I'm going to proceed with the knowns that I can easily pick off in 3, 2, 1. Pressure initial, piece of cake, 100.0. Well, I know that NT, I'm going to say V initial equals nRT over P initial, just rearranging the ideal gas law. I'm going to do the math on that. I'm going to plug in the numbers. What did I get? I get 10.393. That's the same as the last problem. That's where I got that from. You can punch in the numbers, pause the video if you need to. And then let's see, V final. We know that's going to V final here, and I know the trick was multiply by 1,000. So 1, 2, 3, that's 100 liters. And now I could actually, let's see, what do we know here? I know the initial temperature is 1,000. It expands adiabatically. What was adiabatically? S, entropy is constant. That doesn't help us much. But I also know Qn is equal to 0. And lastly, I know P initial, V initial to the gamma is equal to P final, V final to the gamma. All right, so while Qn, that's going to help me at the end of the problem. Entropy, we're not talking about that until the end of next chapter. So this result is probably going to be the one that helps us out. So what do we do here? Well, I'm going to take a guess and check because I don't know the temperature range, but I do know it's 1,000 Kelvin. And what's going to happen to the temperature, right? I know that P initial, V initial equals nRT initial, or I guess I could take P final, V final equals nRT final. I'm just trying to think it through a little bit. Well, in this case, the volume goes up. All right, when the volume goes up, the gas work is being done by the gas. So we expect somehow the volume's going to go up, the gas is going to do work. Delta E internal equals Q in minus work by. Aha! I've got it! I know that there's no Q in because it's adiabatic. I know that the gas is doing positive work, so E internal should go down. That means temperature should go down, right? If this is 0 and this is positive, negative of a positive, this should be negative. That means temperature should go down. I'm going to assume for right now that the temperature stays within a single range. On test questions, I try to do that for you because let's face it, these are hard enough as it is. If you had a temperature, if the range was changing, that becomes a lot harder. You can do that problem yourself. I'm going to go way over here, right? And I'm going to focus on this stuff over here. Ignore this is the last problem. We're going to assume that we're probably going to be in this temperature range. And what we can check is if T final is above 200, we're good. So I'm going to assume F is 5, and that gets us back our same numbers, right? Why am I always doing F equals 5? Because a lot of real life problems focus on diatomic gases with 5 degrees of freedom. That's why I'm hammering on that. I'm trying to be reality based here. On an exam, what might I do? I might mess with you and pick a different temperature range just to see if you're paying attention, okay? So always check this on the test. So we're going to check, is it 5? If so, gamma would be 7 over 5, which is equal to 1.4. Let's use this trick to try and find the final volume and the final pressure and check the final temperature. So we can use this and this together with that degrees of freedom. Oh my gosh, there's a lot going on. The adiabatic process is a little bit tricky. All right. Well, let's get to work here. P initial, V initial. In this case, let's think if I need to worry about the units. Well, if I'm trying to solve for P final, rearranging this, what do I get? P final is equal to P initial times V initial over V final quantity to the gamma. Take a second, right? You divide this over and then, right, you can put this is equivalent to that. So now think, do I need to worry about the units? No. All right, so let's punch in our numbers real quick. P initial was 100. Okay, so I'm just gonna write this out so I don't screw it up. V initial is 10.393. V final is 100. And then raised to the gamma, which is 1.4. All right, let's see what we get. 10.393 divide by 100. I'm going to raise that to 1.4. Then I'm going to multiply by 100. And I got 4.202 or so. How many sig figs? 4. This one had 4. So I guess I better write it to an extra digit. 4.2018 kilopascals. All right, and that matches up to what I had found earlier. Well, now I could use this result to check it. There's another result that's derived in, I think, problem 19.17 that directly relates to the temperature. So if you had that memorized, I just like to use these. I remember this one and that one, and I just go to work. So let's do this. I know P initial, V initial. I know P final, V final. I can solve for T final. What am I going to get here? T final is equal to T initial times the quantity P final, V final over P initial, V initial. You'll see this a lot where you get those PV combos. So I'm going to go ahead and what was T initial? 1000. And then I know P final is this, you know what, I'm going to color code this one so I don't screw it up. All right, so I'm going to punch in the numbers. You guys can do this too, ratio. So 1000 times P final, V final. Well, that's just shifted 2, that's 420.18 divided by P initial, V initial. Well, that's just shifted 2, that's just 1039.3, 404.3. So what did I get here? T final equals 404.3 Kelvin. Why am I doing this again? I'm verifying we're in the right temperature range. Check. So that means my assumption was valid. Now I feel confident in these numbers. Now I can go ahead and proceed and use those for the rest of the problem if I need it. So this one was, remember this is F over 2 times R, which ends up being 20.785. This one ends up being this number plus R, which is 28. Wait, I'm screwing it up. I'm screwing this up. I want to check if it, let's just do it. 20.785 plus 8.314, 29.099, good. And you probably are smart enough to realize, wait a minute, I don't even need this one. This one can sometimes come in handy because we can use our shortcut. But this one, we don't have any constant pressure on this particular process. This comes in handy if you have cycles where maybe one process is adiabatic, one's isothermal, one's isobaric, and one's isochoric. But so here, we don't even need this. I didn't need to bother with that. All right, why don't we draw some points and then we'll try to get the curvature right. So 10 and 100 approximately. So 10 and 100, there's point A. Now point B is a little bit different. It's 4 and 100. So that's a real low. There's halfway and then a little lower. So there's point B. Now the question becomes, can I get another point in there? So the only easy way to do this, I guess, would probably be to use this one. So what if we had 30 liters? So let's assume, let's do check V3 equals 30 liters. So I'm going to punch that into here and I'll get pressure 3 equals, and you could use either the initials or the finals, but so I'm going to go ahead and say this V3 is the final, so that would give me P initial, which was 100, times V initial, which was 10.393 liters, and then I want to use 30 liters. So let's just get a third point really quick. 10.393 divide by 30, x to the y, 1.4 times 100. I got 22.67. Is that what I found before? Yes, it is. 22.67. Why am I drawing this? I'm just trying to figure out how curvy the curve is. So if I come out here to 1, 2, 3, 30 liters, I should be at 10, 20, and about a fifth of that. So I'll just call that 0.3. Whoa, so you can see, and maybe if I just have this on the screen at the same time, it's worth it. All right. So notice this one dips way lower. It's not perfect, obviously, but so for comparison, right, at 20, whoops, at 30, what we're doing, we're comparing 30 here. Right, this was about 35 at 30, whereas this one is way down here at 22 at 30. So hopefully that helps you kind of see. They don't, yeah. So if you look in the workbook solutions for this problem, I've got them plotted on the same plot, so it's easier to compare them. But generally what I want you to remember is, if you're comparing an isothermal process to an adiabatic process, the adiabatic goes lower. You can clearly see it at the end point, right? So for the same type of expansion, the same amount of delta V, the adiabatic's going to drop lower, all right? All right, so in this case, let's get back to what we're doing over here. Well, maybe before we can guess. What do you think should be true about the work done by this process compared to the work done by that process? This one has less area, it's lower. We expect the work done by should be less than 2300 here, all right? And so what about Q in? It's 0. What about the change in internal energy? Right? Well, let's think. Let's go back here. Come on. Come on. Clicking buttons, nothing happening. Look, the temperature drops. If the temperature drops, E internal should be negative. All right, so let's go ahead and finish this problem out by figuring out the first law stuff. So here we go. Notice how handy these units are. Kilopascals and liters giving joules. It's kind of handy. So what are we trying to figure out now? Q in joules for an adiabatic process is 0. We could do work done by the adiabatic process. And we could do delta E internal. All right. So what are our tricks? Shortcut. Delta E internal is equal to N CV delta T for all processes. All right. I know N, I know CV. Oh shoot, I didn't write those temperatures down. Crap. What were they? Let me just look them up really quick. Okay, so I think I had T, oh, I might have it in my calculator, right? Yeah, T final was equal to 404.3 Kelvin. All right, got it. T initial is 1,000. So delta T, we can get that. Delta T is 404, oops, just this one, minus 1,000, negative 595.7, off in that sig fig. So we expect 3 on this answer. CV is known, so times 0.1250 times CV, 20.785, negative 1547.7. And we said off in the third sig fig here. Third sig fig. So we're only good to the tens column. All right, this makes sense. Temperature goes down, delta T is negative. We expect delta E is negative. Could I get work done by? Well, if this is 0, work done by the gas had better be the opposite. Notice we get work done by equals negative delta E internal for an adiabatic process. So I could get the answer right now. It should be positive 1547.7 third sig fig. Think, does the sign make sense? This process is going the normal math direction. Area under the curve should be positive. Work done by should be positive. Delta V is positive. The gas is expanding. It's doing work on the piston. Makes sense. Now, as a check, I know P initial, V initial to the gamma equals some number. Let's just call that number K. I know these values, I could punch that in. And if you want, let's do that really quick. So P initial is 100 times V initial times 10.393 raised to the 1.4, 26.512. Wait, 2,651.2. Okay, so that's my constant. I don't know the units on it. It's gonna be some weird ass unit to the 1.4, whatever. But it's some number. I'm not gonna worry about the units. And I'm running out of space here, so I'm gonna do this. All right, now check. We have P V to the gamma equals that constant. So what is P equal to? It's K over V to the gamma. Now I could do the work done by equals the integral of P dV. I could plug this in. And when you integrate, what are we going to get here? Well, this is the constant pulls out, and then it's the integral of v to the gamma minus, to the negative gamma dv. When I do that, it's going to be k. You raise the power, right? So it's negative gamma plus 1, and then you divide by the new power. Negative gamma plus 1. Then we have to evaluate that at initial and final. When I do that, this ends up being, well, I guess I'm kind of in a, you could keep working this out and, well, all right, let's do it. Stop being lazy, Rob. So I'm going to say it's K over, actually, I'm going to do it this way. 1 over 1 minus gamma, that's this term. And then I'm going to say it's K times V final to the negative gamma minus 1, plus 1, minus K times V initial to the negative gamma plus 1. If we are clever at this stage, we can make it look a lot prettier. The trick is P initial, V initial to the gamma equals some constant, but isn't that same constant also P final, V final to the gamma? So what we do is we plug in K as P final, V final to the gamma for the first term, and we plug in K is P initial, V initial to the gamma for the second term. And when you do that, what do we get here? This is just P final, V final. And this term is just P initial, V initial. So there, we did it. Now, if you take the time to punch in these numbers, we should get the same result. So, let's take a second to do that. I'm going to do the part inside the brackets first. P final, V final. So that's 100 times 4.2018. Remember, liter times kilopascal gives me joules, so I don't have to change the units here. And then I'm going to subtract off P initial, V initial. 100 times 10.393. So I get negative 619.12. Over 1 minus gamma. Well, 1 minus gamma, that's just 0.4, because this is 1.4. So then when I punch that in, I just divide that by negative 0.4, and I get back this result. All right, so looking good. So, and maybe what I'll do is I'll write the final results here, so we can do the final comparison. Qn equals 0. Work by is 1550. And delta E internal was negative 1550. And then I'll just scoot the screen over so you can compare. Let me get out of the way. Let me turn off the screen. Oh, geez. All right, so there you go. Comparing these, we expect less work, but they're both positive because they're both going this way. The temperature drops in this case, so the energy goes down, but there's no heat added. In this one, you add heat to keep the temperature from dropping. All right, that's a long one, but adiabatic is the